Hello, today we're talking about herd immunity and going over the rest of those notes that you were supposed to do over examining the influence of vaccinations on the spread of influenza. So we're given our three different scenarios with our different R naughts. Remember, the R naught refers to how spreadable the disease is. So the average number of people that one infected person will then infect. So you have three different R naughts for these different scenarios that I gave you last time. Scenario A, the R naught is 2.2. Scenario B, the R naught is 1.88. And scenario C, the R naught is 1.43. And then you're supposed to watch that video and about how the flu vaccine works, first of all, but also about how herd immunity works. And it talked about measles vaccines and an outbreak that occurred in Brooklyn, New York. So most of the population was vaccinated in Brooklyn, New York. So this wasn't much of an issue for them. But if a lot of the population wasn't vaccinated, that could have become a serious epidemic. And so that's how that works, is if a lot of the community is vaccinated, even if you have vulnerable people in the population like babies and very elderly people who cannot get the vaccine because their immune systems are too fragile or immunocompromised, or their immune systems aren't going to work, it's just not going to work, so they don't get the vaccine. Okay, so if the rest of us get vaccinated, what herd immunity is that us vaccinated people, because we're not spreading the disease, we don't really get sick with it, so we're not spreading it for a long period of time. That means that we're not giving it to the vulnerable people who can't get the vaccination in the first place. So if I were to be vaccinated for measles, and I were to come in contact with a sick person who had measles, the virus might stick to my skin or might get on me, just like it would normally, but my immune system would attack it so quickly that it wouldn't infect, it wouldn't replicate in my cells. It wouldn't be an issue. I wouldn't be passing it on, even if I went to an older person and visited an older person, or I visited a baby later in that day. It'd be okay because I wouldn't be spreading it. And so that's what herd immunity states. And this is how it prevents epidemics. The more people are vaccinated, the better chance you have at not having an epidemic take place. For the coronavirus specifically, because none of us had immunity to it, that's why this was so dangerous. There's no vaccine for it. So that's why this outbreak was so easy to take hold, and because it's so transmissible. So it is a very high R naught. Okay, so let's talk about how to calculate the herd immunity threshold. So what the herd immunity threshold is whatever number you get out of here. If I were to get a 0.5, which means 50%, that means 50% of that population would need to be vaccinated in order to prevent an epidemic. So if you get 0.7 out of this calculation, 0.7 means 70% of the population has to be vaccinated in order to prevent an epidemic. So the higher the number you get, the more people need to be vaccinated. And honestly, the less realistic that is. So the lower number you have of a herd immunity threshold, the better chance you have at preventing that epidemic in the first place. Because if, say, only 35% of the population needs to be vaccinated to prevent it, then great, that's a higher chance of no epidemic occurring. Okay, so you have your calculation for the herd immunity threshold, which is IC equals, this is the herd immunity threshold is IC, and it gives you that key on that front page, 1 minus 1 over R naught. So all you do to calculate this for each scenario is just plug in your different R naughts that you have for each scenario. So for scenario 1, it was 2.2. So you would just plug in, there we go, 1 minus 1 over 2.2 into your calculator. And you would have gotten 0.55 for scenario A, 0.47 for scenario B, and 0.3 for scenario C. So which one had the lowest R naught? It was scenario A. Scenario C. Scenario C had the lowest R naught, meaning that virus that specific flu virus that we're talking about, was not as transmissible. It's less spreadable. Scenario A was like the worst case scenario in this case of possibilities, where you have 2.2. That's the highest R naught you have, and therefore you're going to need more people to be vaccinated. So the higher number R naught you have, the higher number of people need to be vaccinated to prevent the epidemic. So scenario A was 0.55. That's the highest. So that means 55% of the population must be vaccinated if this epidemic, to prevent the epidemic from taking hold. Scenario C, on the other hand, is much lower, 0.3. That means 30%. Only 30% of the population needs to have that vaccine in order for that epidemic to not occur. Okay, so scenario C is like best case. Scenario B is kind of like in the middle. 47% of the population needs to have the vaccination. And then it goes into how this calculation is great because it tells you theoretically how much, if the vaccine were 100% effective all the time, the type of herd immunity you would need. But the most realistic calculation is if the vaccine doesn't work. Because if you watch the other video, for influenza vaccines, what they do is they predict which types of proteins are going to be on the outside for this, for the next season's epidemic. And then they make vaccinations based on what their predictions say with complex computer models. And of course, it doesn't, like this season's flu vaccine was not very effective in influenza B. It protected very well against influenza A, which H1N1 is a type of influenza A. That's the swine flu. It's a type of influenza A. And it protected really well against influenza A, but influenza B, people were more susceptible to. So that's what more people ended up getting sick with this season. So they were not as protected on the influenza B side. So it was less effective there. However, everyone was still protected very well against influenza A, so still worthwhile in getting the immunization because you're still protected. And even if you get the flu shot, you're still somewhat protected against any type of influenza. You're probably going to fight the disease faster because your immune system has at least a slightly recognizes that vaccine that you're coming, or that virus that you're coming in contact, if you do come in contact with it. Okay, so then you have, say we have an effectiveness of 0.65, okay? So like say this year's flu was 0.65. Well, now the real calculation we need to do is VC, which is, takes into account the effectiveness. So that's when you take your IC, your herd immunity threshold that we just calculated, and put it over E, so the effectiveness. The effectiveness that they said in this scenario was 0.65. So you just plug in each of your IC values that you got for each scenario over the 0.65, which they gave us for E, which means it was 65% effective. Okay, so for VC, you should have gotten, and they just are giving us a hypothetical H1N1 scenario. Scenario A would have been 0.85, scenario B would have been 0.72, and scenario C would have been 0.46. So this is the herd immunity, the real herd immunity, taking into account the effectiveness of the vaccine that's needed. Okay, so in this case, scenario A, which had a really high R naught, so our virus was really spreadable, 0.85. So to prevent this vaccination, or this virus from taking hold and creating an epidemic, 85% of the population needs to be vaccinated, and that's pretty hefty. Scenario B, 72, still very high. And scenario C, with our R naught of only 1.43, so our lowest R naught, our less spreadable virus, is only 0.46. Only 0.46, so only 46% of the population needs that vaccine to prevent the epidemic. So when we're looking at this and thinking about, okay, well, which one is most preventable? Scenario C is most preventable because you can get 46%, only 46% needs to be vaccinated. And that virus, and that's because that virus has a really low R naught. It has a less spreadable influence. Whereas scenario A, if you have a really, really spreadable disease, spreadable virus, 85% of that of the population needs to be vaccinated. However, if all these people get vaccinated, that prevents the epidemic from ever occurring, and it protects all vulnerable populations. Okay? That's it for today. That's also it for the content this week. So you will have a quiz over everything that we've gone over this week. That includes how infection cycles of the coronavirus, just what we've talked about, no more in depth than what we talked about. You will have to understand herd immunity and vaccinations. And that would be it for this week. Okay? So don't forget to take your quiz tomorrow. It'll be also timed, same format as last time. If you guys have any questions, you have to send them my way, because I know you will have questions while you're doing these activities, but if you don't ask them to me or email them to me, then I can't get you the answers. Also, if you want to set up a one-on-one Zoom, if you're really struggling and you really aren't sure what to do, we can set up a one-on-one Zoom meeting. You guys just have to tell me what you need, what you're struggling with. Okay, it's on your guys' responsibility, because I'm not there to help you physically, but you guys have to advocate for yourselves and let me know when you're struggling and what you're struggling with. Okay, I'm here for you. I got you. You just gotta let me know. All right, you guys have a great day, and don't forget about your quiz tomorrow. Bye.